Well, I would like to take this opportunity to thank the organizers for inviting me here to Finland. I do not. Yes. I do not know too much of the Finnish language, and probably what I have written here exhausts my knowledge. But it does give a summary of the message I have to give. It says, now the people who are from Finland will surely laugh, but I must give them an opportunity to do so as quickly as possible. Anoka niin teille annetaan, etsike niin te löydätte, kulkutakaa niin teille avataan. I don't know, is that, how bad is it?
Very bad.
Oh, I see. What it means is this. The famous quotation from Jesus: ask and it will be given you, seek and you will find, knock and it will be open to you. Well, what I'm trying to say is that the purpose of collecting data, in my opinion, cannot simply be to analyze it. There has to be a bigger purpose. Purpose has to be to solve some scientific problem. And reason why one analyzes data is so that the analysis be applicable. If the model that we are using is wrong, then irrespective of how correct our answer is under that assumed model, the analysis will not be to the point. It will be wrong. So, well, this can happen also in the context of linear models. And so here, today I will talk in this context. We have a linear model, expected value of y equal to a1 xc1. xc1 are the parameters, and variances as usual. Now a linear model is an assertion about the true situation. That assertion may or may not be true. Similarly, an optimal design based on this linear model is truly optimal if the assertion is correct. Otherwise, the optimality may be an illusion, being a correct solution to a wrong problem. Therefore, unless one is reasonably certain about the model, I believe that too much of fancy academic work on computation of the exact optimal design may not be called for. In a given situation, instead of asserting one model, it is more likely that one out of a family of models is the correct model. So here I have written a family of models, and if this part a to I, xc to I is ignored, then we will have the original model. So if the original model was used, then there will be a bias, and the bias part will be this part which I have indicated in red. Now these models can all be combined into a single expression and written in this form, where xc2I, these parameters are subsets of a vector xc2, and a2 then will have the columns a to I as a set of subcolumns. And again, a1 and a2 are known design matrices. And I will consider the case where each of these xc2I have k parameters in them, and so that in xc2 all choices of k parameters can be considered, and each one will give a model, so that the number of choices will be nu2 choose k, where nu2 is the element is the number of elements in xc2. Now suppose that there exists a number k such that at most k elements of xc2 are non-zero. However, which elements of xc2 are actually non-negligible is not known. So this is a more realistic formulation of the actual problem. See, we are not asserting one model and fanatically pursuing it, but we are asserting a family of models, and the purpose of the design therefore is a twofold purpose: to find out which model is correct, and then also to accurately estimate parameters under that model. So the problem is to identify the non-zero elements of xc2 and estimate them along with xc1. The non-zero elements of xc2 will correspond to the actual model that is correct. So as I just now said, the design objectives ought to be twofold. Number one, identify the bias, which is equivalent to saying that find out the source of the bias, which means find out the correct model. That should be the first objective of a design, and the second objective ought to be to estimate parameters accurately, and that of course is the idea behind the theory of optimal design. The theory of optimal design is a theory which gives you optimal designs under the model that you have assumed. It does not prove to you that the model that you have assumed is correct. If we pursue only one attribute, namely estimating parameter accurately, then such a theory of design should be called single attribute dominant design theory. And I have marked out S, A and D, and that makes the word sad, because see, it may produce some sadness later on. when you see you make forecasts on the basis of your assumed model and on the basis of the optimal design that you use, and you find that the forecasts do not match with the reality, then you will be sad. Now, the question is how to deal with bias. Professor Box, you see, has been knocking at this problem for a long time, and Box and Draper, Professor Draper is here. See, they have made important contributions to that field. Their basic idea, however, is to choose a design in such a way that the bias is minimized. Of course, that assumes, that you know the source of the bias to a large extent. That's one problem with that approach. Another problem is this, that what you receive with one hand, you give away by the other. In other words, you see, the accuracy that you develop, because you have reduced the bias somewhat, you lose that, you see, from the point of view of variance. So, and also...
Forgive me for objecting at this point, but you are not stating correctly what you did. The objections you are now making to what we did are not correct objections.
All right, we can, after my talk we can discuss that. I had not completed it. Actually, as I see it, the bigger problem in that approach is that unless we really know what the bias is, we have not determined the correct model, and to me, unless the correct model is known, the scientific problem that we are trying to solve has not been solved. Now, Professor Box and Draper don't have just one paper, and in 1 minute I cannot summarize all the things that they have said. But this is remark of mine will certainly hold on all such attempts, not only by them but by anybody else. There are a lot of papers by other people also on this. But all those papers you see, they try to minimize the bias in some sense. And my point is that we need to know the correct model. The problem is not to have some model that is not correct and then to hope that the bias is reduced. But the problem is to have the correct model itself. So thinking of this thing, you see, I considered the problem of designing the experiment in such a way that we can identify the source and estimate the bias. Now, so we consider technique of estimation, and this result I proved long ago. This is the fundamental necessary condition that bias can be identified. The condition is that the rank of the matrix A1, A2 naught has to be equal to nu1 plus 2k for every submatrix A2 naught of size n by 2k which is contained in the matrix A2. So just so that you understand this notation, you see A1 XC1, A1 is the coefficient matrix which goes with XC1. XC1 we want to estimate. The part of XC2 which is non-zero has to be identified. So that is how A1 and A2 arise there. And here I am saying that for every submatrix A2 naught which has 2k columns, this condition must hold. And if this condition holds, then it can be shown that in a reasonable sense, in fact the condition is also sufficient, you can identify the source of the bias. A design that satisfies this condition is usually called a search design. Now in today's talk, by the way, a lot of research has been done on search designs over the last 15 years. There are a large number of papers, but the question arises, can we do the identification with a good probability or not? So this question was considered by me and some people in the late 70s, and three kinds of studies were made. One kind of study was the theoretical formulation of the problem and of the techniques of identification. That is what I am going to discuss today. The second was a particular technique which was theoretically developed. Those results are published in the Journal of Multivariate Analysis. And the third one was Monte Carlo work. The Monte Carlo work showed that the techniques that I am going to discuss today are probably the best techniques. So that prompted me to consider these techniques theoretically, and this is what I am going to discuss today. So today the talk is concerned with the probability of correct classification. Alright, so this is the model. Technique 1 says that you calculate the sum of squares due to error under the ith model. Ith model corresponds to some subset of k parameters out of XC2, and then choose that value of I for which the sum of squares due to error is minimized. That is the decision rule for selecting the ith model as the correct one. And here I have just written down the expression for the sum of squares due to error under the ith model. Technique 2 is this. I partition y into two parts, y1 and y2. y1 is of size nu1 prime and y2 is of size nu2 prime. And correspondingly a1, a2, they get divided into these four. And we assume that rank of a1 is nu1. That assumption is necessary, otherwise we cannot estimate xc1. Now I define the matrix a11 star by this equation, c0 then by this equation, and a21 and a11 are here. So using them I have this expression. This is a positive definite matrix, and k is such that k is a square matrix such that kk prime equals this. Then I consider the random vector z0 defined by this equation here, and c defined by this, and z defined by this, and then it can be shown that expected value of z is cxc2 and variance of z is sigma square times I. Now what has been achieved by these transformations is that I have reduced the model to what is called a pure search model, in the sense that here in the expectation of z only the vector xc2 occurs, out of which the identification has to be done. We have cleared ourselves of this vector xc1. You see that this vector xc1 is involved in this computation here, but here xc1 won't be involved, so that is the idea. Now this is the rank condition. Now this is a basic theorem. It says that this rank condition holds if it holds, and if this condition holds, then C has the property P2K, which says that every set of 2K columns is linearly independent. Secondly, if C has P2K, then this rank condition holds. Now this is an important theorem because it allows us to study the problem under the reduced model where only the matrix C has to be considered. So C is K inverse times C naught. C naught is of this size, and C naught naught is a submatrix with 2K columns inside C naught, and with the C naught naught so defined, this basic rank condition implies this rank condition, and these results hold. If this rank condition holds, then rank of C naught naught is 2K if and only if the rows of these are contained in the row space of this matrix. If a star holds this basic condition, then C has the property P2K if this result if this condition holds. Nu1 prime is equal to nu1. Remember that nu1 is this number of parameters in xc1, and nu1 prime is the size of the vector y1. And if this holds, then y can be rearranged so that C naught and C have P2K. Now that theorem is very important. Basically, it is allowing us to do the kind of investigation that we need to do. So now we consider that same pure search model that I just showed on the other transparency. Ith model is now this one, and we compute the sum of squares due to error in this case, and it will be this, and the decision rule is similarly to choose that I for which the sum of squares is minimum. So this is the technique number 2. So technique number 2 involves taking a y1 vector, using that to eliminate xc1, and then continuing with the search problem. Then technique 3, you see, eliminates xc1 directly by considering this operator g, and if P is an orthogonal matrix which diagonalizes G, then D will have to be of this form, and this part is denoted by D1 and then there is 0. Then if xc2 is defined by this, expected value of xc2 will be this thing times xc2 and so on. So that again here we have gotten rid of xc1, and this is a reduced pure search model, and again we can consider sum of squares due to error and so on, and define a technique based on that. This theorem says that techniques 1 and 3 are equivalent. Now let delta be this matrix, and you remember A11 star is A11 prime, A11 inverse, A11 prime. So if we define delta by that, H by this one, and K is a square matrix, and this result will hold, and then this theorem holds. Delta A1 is 0, H square is idempotent, G and H commute and are equal to H, G minus H is non-negative definite, and if this condition holds, then the three techniques are equivalent. So this study, these set of theorems are on equivalence of these techniques. Now technique 2 has computational advantage because there only the z vector is being considered, which is of a much smaller size. The search linear models, they were introduced by me in 75, and the technique that number 1 was introduced there, technique 2 was introduced in 76, and there is a technique 4 that I said is published in this journal of multivariate analysis. That's quite a multivariate type of technique, but its probability of correct search is lower than the technique that I will discuss today, which is the original technique that I had proposed in 76. So the probability of correct classification under technique 2 is what I will consider today. This is the model. The probability will be this integral where g of z is just the, I am assuming normality, so this is the integrand, and the region R1 will be intersection of these regions. And psi square EI is the sum of squares root of error. So it will be equal to this expression where Ci now we recall will be this thing. A2I is a set of k columns out of the A2 matrix, and Z is defined by this. And remember C matrix was equal to this thing, and expected value of Y originally was this. A1, A2 were partitioned in this way and Y was partitioned this way. Kk prime equals this. I have just written this down again to recall for you all these kinds of expressions. So now what do we see here? We see that to study this integral, I need to look into the properties of the matrix C, because see it is the C whose submatrices Ci are occurring here in psi square EI and defining this quadratic form, and here each of these quadratic forms has to be greater than psi square E1, which will correspond to C1, and the number of such regions you see is mu to choose k. So I have an intersection of that many regions, each region being defined by an inequality between two quadratic forms. This problem I had discussed in some conferences in multivariate analysis and so on. The general solution to this problem is not yet known, it's not solved because of this complexity of this region R1. However, I have succeeded in solving the problems for this problem for most of the search designs that are in the literature. I will show to you how. Before that, I consider this example from 2 to the m factorial experiments. XC1, suppose it consists of mu manifests in two-factor interactions, then mu1 will have this value, XC2 will have the remaining effects, and so mu2 will be this value, and we will consider k equal to 1. For example, when n equal to 5, mu1 will be 16, and XC1 and XC2 are as before, so mu2 will be 10, k equal to 1, and T will denote the design. Design is simply a set of level combinations. We will consider in our example, now the theory that I have is a general theory, but I will exemplify that theory by this example. So in the example there are 21 treatments and they are of weights 0, 2, 4 and 1, and weight of a treatment is the number of factors which are at level 1 in a particular treatment. So for my example, this is the design that I am considering. These 16 treatments here form an orthogonal array of system 4, half replicate of a 2 to the 5, and then this also, these treatments. This is a design that was given by Ghosh and myself around 1977, and it satisfies that basic rank condition. Now the expected value of observations on these is given by this matrix. As usual, the plus and minus are defined, and so this matrix is A11, this is A12, this is A21, A22, and this design happens to be a balanced array of 4 strands. Now, because of that reason, you see, we can use certain things from matrix theory. The Bose-Messner algebras are defined corresponding to the ordinary partially balanced association schemes. Then there are generalizations of that due to Bose and myself called multidimensional partially balanced association schemes, which gives rise to the algebra of Bose and myself. And because of lack of time, I will not define this scheme, but it's a well-known scheme, and this scheme gives rise to certain matrices of large sizes, and these matrices have the property that the product of any two of them is a linear combination of all of them. That is why they are called an algebra. And the algebra of Bose and myself is non-commutative, and it contains the Bose-Messner algebra within it, which is commutative. The spectrum of matrices in some of these algebras was studied by Chopra and myself in many papers in analysis, statistics and elsewhere. And then there is this factorial subassembly association scheme, which is an association scheme in which subsets of integers are supposed to be GHK associates, depending upon how many integers are in each set and how many are there in the intersection. Now, for the factorial association scheme, the algebra of Bose and myself was further studied by many Japanese statisticians, and some of the most important results concern the Yamamoto, Fujii, Hamada ideals inside the Bose-Srivastava algebras. And so using all this kind of thing, it can be shown firstly that all these matrices that are arising there, they are in my algebra, and because of that I can conclude the matrix C will have this form. You see that C is a result of a lot of transformation. There is square rooting and so on, and we have multiplied and inverted and so on, but through all that thing one can go through. But because of the properties of these algebras, it can be shown that C will be of this form, and where A is root 2 and B is minus root 2. And now for that kind of a matrix C, the region of integration reduces to this form, and then theorem 4.3 holds, which says that the probability of correct identification is phi of theta root 2 to the power 5 plus phi of minus theta root 2 to the power 5, where phi of x is the cumulative distribution function, the normal distribution. It turns out, therefore, that if theta, the value of the non-negligible parameter, is just 2 times the standard deviation, that is quite low, even then the probability of correct search, if we know it exactly, it is 98.9%. So, well, this is my last transparency here. This is just an example to show how the classical half replicate will mislead you, because you see there is compounding present because of the defining equation. The equation that define the half replicate, and so if the maximum yield is 27 and these runs give the maximum yield, what it will show to you is that something else is giving the maximum yield and so on. It will be misleading. The optimal treatment combination will not look optimal. Something that is quite bad may look optimal. So the reason I am saying this is that it is worth seeking, worth finding out the source of the bias and correcting for it. Otherwise, you see, if we are using this in industry, we will be producing product which is not of the highest quality, because it is being produced under non-optimal conditions, because our analysis has misled us. So, just coming back to my original slogan, seek and you will find. In other words, it is not true that we have to assert a model and just live with it, and the only thing that we have to do is just to make an optimal design under the model and try to find the best techniques of inference under the model. I think a better procedure is to do experiments or collect data in such a way that competing models could also be examined under the data and studied. Thank you.